teaching to begin, or starting off on the whiteboard?
Nope, teaching.
Teaching, yes, sir.
Yep. Hi, sir.
Good afternoon.
Afternoon.
Did you finish it?
Just a quick question. Could you come around, I'll read over your shoulder.
That's why I got it.
So, what the,
Well, let's compare the original problem. Maybe it's a missed copy. You got a copy of the test here? I don't. I gotta look it up. Well, it's somebody else.
2.5 times 10,
And this is
18.
under. We'll find it here. Here, my name. Yeah, you miscopied the problem. Yeah, you miscopied the problem. It looks like it's a times problem. This should be times. We'll take a look at the test to verify that. That's what it looks like right now.
7, 7.5.
Here's a copy of the test. We verify the problem. That get better next week.
Oh, yeah, yeah, sorry.
start, so the class grades are on the front board, if you want to check your grade with your classmates. Here's the class. So we are collecting homework before class starts, not after, so any homework would be a good time to put it up in the pile.
So you think the homework will?
A1, A2 only.
Only A1 and 2?
All right, A1, A2 only. We do have the stapler up here. Let me see. That's Frito. So 2 minutes for start. So if you're engaged in some other activity, please try to time it so you reach a good stopping point. 2 minutes. Hi, Dylan. Fine, yourself?
So,
Yes. seconds now. What do you think about closing down text and nothing pencils? Ready? Thank you. Okay, thanks everybody, I'd like to welcome you. Hi. And it's okay, you're on time. And so the first item of business, of course, is that I have returned your test ones to you, and given you a quick moment to look them over. Sometimes it's a very quick moment. And these are the class grades in the front board here, so you can compare how you came in with the rest of the class, if you care to. So I recommended that you ace this test so that it balances out with test 2, which is hard, and test 3, which is very hard. But, evening, sir, how are you tonight? Yeah, but test 4 is easier when you get there. So the next 2 tests are not. So you wanted to get a good score in this one so you could average out. And apparently 8 people believed me, and they got solid 90-something on it. And if you don't throw chairs at other people, this is a participation course. So we do expect you to do your share in the whiteboards. And as long as you continue to come in with your homework done, do your share in the whiteboards and all those other good types of things, professionalism, homework, punctuality, and attitude, then you're going to be able to get an A with an 88.5 on your test, and a B with a 76. So you see we have got 9.5 A's and 1.5 B's and 2 high C's. So I'm gratified. Everyone clearly belongs on this side of the door, should be in this class, so we can proceed full speed ahead. Okay? What I need you to do now is to take the test I just gave you and put a circle around your grade. Now that means that you saw the test, doesn't necessarily mean you agree with the score. And you can look at the test as long as you want after class, but I'll take them back now. Two tests here. Okay. Thank you. And one more. Thank you. Okay, so today's business is dealing with Chapter 2. And as you see, there's 4 sections. So we're going to pick up the pace of the course a little bit, since we're winding down week 3 now. And we're going to do all 4 sections of Chapter 2 tonight, which means the presentation is a little heavy. So for that reason, I'm going to start with some presentation, then we'll have some counterbalance, do some whiteboards, and then we'll wind up with more presentation. Before I do that though, I'd like to revert to the handout I gave you last time on scientific notation. So could we use that for just a moment? I didn't get a chance to present a couple of examples, and it's only fair that I do that. So I'm going to write a problem down on the board. So please confirm my memory that we haven't looked at this problem before? No. Okay. Now I'd like you to try to punch this into your calculator. And unless you've got a fancy dancy calculator, you're very liable to get a message, exceeds capacity of this calculator, error cannot do, because it's got too many digits in it, or else it will automatically convert to scientific notation, one or the other. Now let's try this problem in scientific notation. We have 8 times 10 to the 9 times 12 times 10 to the 9. And if I rearrange that, it's 8 times 12 times 10 to the 9 times 10 to the 9. So now you see we have something that any calculator can do, even the one in the Cheerios box, very easily. And that's the reason we use scientific notation, because in astronomy we have very large numbers. These are small. And in DNA studies we have very small numbers, atomic physics, nuclei, and things of that sort. So for very large and very small numbers, then what you do is you just write something up here like this. So Derek, we need you to join the class. I hope you're writing this down. Okay, hopefully, good. So what we want to do is collect the strength of the number in the powers of 10, and all that leaves is some coefficients that are easy to calculate. So we get 96 times 10 to the 18 for our answer. So that's how we do it. So now I'd like you to do one for me, no pencils, on this worksheet that you're working with, number 79.
You have any-
I'll try to dig one up. So we gave you one last time, right? Just got
I
lost.
think I left it on.
Oh, you left it in the chair, okay. So I'll write it on the board, even easier. 2 times 10 to the 3, 3 times 10 squared. So no pencils. The answer is 6 times 10 to the 5th. 6 times 10 to the 5th. Okay. So the next problem is 86. 20 over 10, 20 over 15. No pencils, the answer is,
10 times 10 to the fifth.
one more time?
10 times 10 to the fifth.
One more time.
2 times 10 to the
Two.
fifth.
Yeah.
Oh,
Should have let you use a calculator, I'm sorry. 20 divided by 10 is approximately 2. So we have 2 times 10 to the 5th. Okay. Now, one more I'm gonna put up. 2, 3, 4, 5, 6, 7. 6, 7. Is 102. And so let's get some pronunciation, calculators permitted. And this answer is Dylan.
6 times 10 to the negative 11.
Any support for 6 times 10 to the negative 11? Any support for 6 times, no support, Dylan.
No?
Emilio,
6 times 10. Oh yeah, 6 times 10 to negative 4.
6 times 10 to the negative 12, any support? Two people, let's look for more answers. You either got an answer or you support one. Darius, what you get? Okay. Mercedes, you have an answer? Same, okay, any support for this number? What was the number again? 6 times 10 to the minus 12. Raise your hand if you support it. Keep working if you don't. Alex, your number?
6 times 10 to the negative 13.
Derek, your number, please.
I'm working this out. Just want to figure it out.
Okay, Kelly, number?
1 second.
Okay. Well, let's change the scientific notation. The top is going to be 9.6 times 10 to what power?
Negative 8.
Negative 8.
3, 6, 8. 10 to the minus 8, agreed? The bottom's going to be 1.6 times 10 to the 4th. So we divide 9.6 times 1.6, we all agree we get 6. Now this is times a rule, using the rule, a to the n over a to the m equals a to the n minus m. So 10 to the minus 8 over 10 to the 4 equals 10 to the minus 8 minus 4, which is?
Negative 12.
That's right. Okay, so we agree on the answer, 6.0 times 10 to the minus 12. And the last one that we're going to do is number 110. You can get started, and I'm going to write it on the board anyway. 1.2 times 10 to the 6. Second number, 8.7 times 10 to the minus 2. And on the bottom, 2 9 times 10 to the 6. And the last number is 3 times 10 to the minus 3. Okay, so let's go and calculate this guy. Momoko, do you have an answer?
I'm still working.
Oh, okay. So Jeremiah,
I have 1.2 times 10 to the first power.
we have a winner, 1.2 times 10 to the first. Does anyone want to see Jeremiah do some steps? No requests. 1.2 times 10 to the first power, we have a winner. Okay, so we're finished with that section of scientific notation now, and we're going to go forward to chapter 2. So I'd like to welcome everyone in the class to the first day of Math 103. Derek, today's the class starts. You're going to say what happened the last 3 weeks. That was arithmetic. Did you see any algebraic equations the last 3 weeks? No, that was warm up, get the rust out, get everybody synced up on the same page, and get you ready for the course. So the course starts today, because today we start doing algebra. And the name of the course is College Algebra. It wasn't like the last 2 or 3 weeks was wasted, because you really did get the rust out and up to speed. And you got some stuff done. So this is the handout for today. And I'd like to start on page 310, please. Start on page 310. So we have two people working out in these pictures. And the caption at the top is called Formulas and Mathematical Models. I'm not sure what you're doing, sir, but let's go to page 310.
I am right here.
Okay, I'm with you. Good. Okay. All right, now let's talk about mathematical models. First, the world is a very complicated place. Reality is incredibly complex. It's so complex that when we do science, we sort of do not deal with reality. Because if we tried to write equations for everything that really happened, our equations would be too complicated to solve. We have no chance of even solving them. We have to simplify. We have to pick some restricted set of parameters out of all the parameters that are out there, and we use those parameters for what's called a model of reality. It's the best we can do. For example, if you're going to want to predict the weather, there are thousands of variables that are involved in what the weather is going to be. What we do is we pick some simplified set, such as barometric pressure, humidity, temperature, wind direction, wind speed. And we pump those variables into an equation, and the equation predicts what the weather is going to be. But the real weather system has thousands of variables, any one of which could make our model wrong. Why do we bother doing it? Because it's all we can do, it's the best we can do. So our predictions, even though they are the predictions of a model and not the predictions of reality, are better than nothing. So we continue making models. Now, scientists sometimes make the mistake of mistaking their model for reality, because they've been working with it every day for 30 years or something like that. And they cross over that line, and they think their model is reality. So they issue such statements as, miracles can't happen because they're not in my model. but is not his model simplified? And therefore could not miracles actually happen in the larger reality? So the results are only as good as the model, and the model is incomplete. So the results are necessarily incomplete also. So science, in its spirit, is very humble. We make hypotheses, and what's the first thing we do? We test them with experiment against reality. We don't have arrogance. We don't know if they're right or wrong, because nature's the boss. Reality's the boss. We test them. So we have these feeble little models, and if they are yielding good results, we tend to make a little bit of belief in them. If we have left out some parameters, we can't really predict what they're going to do. The big consternation right now are the models on global warming. You say, well, why can't they just give a definitive answer? Because there are too many parameters. We can't go back far enough in time to see all the natural cycles. We could be just in a natural cycle. There could be other chemicals involved. The model is too simple to give a definitive answer. There was another real-life incident. Myself, about some number of years ago, I was asked if I wanted to work on the computer program that South Korea has to alert that North Korea has attacked. Attack detection program. And what they do is they pump in some number of variables, like what's the mood today of the leader, are the troops moving, are they oiling the guns? They have all kinds of parameters that they pump in, and the computer spins and spits out the result, just a normal day. Or alert, 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 attack, attack, coming. My question to you is, if you are the commanding general of all the South Korean forces, and a technician comes running in with a report, the computer just said we're under attack, do you counterattack? How many say yes? How many say no? Not going to go with the computer, are you? Because the computer is just a model. Something could have been left out. And if you go with it, and everybody gets wiped out, and it turns out that the model was wrong, that North Korea was not attacking, then I don't think you want to be that person. So it's in our gut not to totally trust our models, because we know they're just models. Now, on this page, 310, we are modeling a mathematical model of the number of calories that you will need for a normal day. And the graph is at the bottom of the page. And you see for each gender we took 6 data points. And then we made a 2-parameter calculation. The only variables that we're feeding into this model are your gender and your age group. Do you feel this model is too simplistic to give believable results of your caloric needs? How many say far too simple? It's leaving out metabolism, afflictions, genetic history, all kinds of other things. So it's far too simple. And that's the truth of all of our models. Unfortunately, they're all too simple. But even the most complicated ones amongst them are simple compared to reality, but they are the best that we can do. So what is going on in this graph at the bottom is that it's a graph of age groups versus caloric needs for particular genders. And once we have these 6 data points, we know that they're real because we measured them. But what about in between the data points? Ages that are in between the data points, like 30.5 years. That's not a data point. But what we do is we draw a smooth line, a smooth curve, connecting the data points, and we assume that the points between the points we really took fall on that curve. It's called model building. And we have an algebraic equation for those curves, because curves have algebraic equations. And they are on the next page, 311. The data for the women conformed to this mathematical model, which is a curve passing through the points. Okay? So Kelly, could you read the mathematical model W, etc.?
W equals negative 66x squared plus 526x plus 1030.
Describes?
Describes the number of calories needed per day. W by women in age group X with moderately active lifestyles. According to the model,
That's
how many
sufficient,
calories?
thank you, we went past the danger zone.
Oh.
Thank you. Okay, Jordan, can you read about the men in the middle, the mathematical model M?
M equals negative 120x squared plus 998x plus 590 describes the number of calories needed per day. M by men in age group X with moderately active lifestyle.
Good, so can everyone in here use their correct model to determine their caloric needs? Use the equation, please. Yeah, I'll try not to write in the sheets because your children will use them if possible. Now, if you get a number like 30,000 or some other ridiculous number, then Dylan, then carefully reread the instructions. So Dylan, did you get your caloric needs?
Haven't finished it yet.
Okay. Como, you have your caloric needs? Emilio, you have your caloric needs? You don't believe it? Esperanza, what's your caloric need? 21,404. Do you think that's reasonable caloric needs for Esperanza? Might be not the recommended range. Mercedes, do you have your caloric needs?
Yes, mine is the same for example, so 2,000.
Well, then this is the trap. This is the reason we're doing this, because your problems of this type are full of traps. So Jordan, could you read for us one more? Describes the number of calories. Please read.
Describes the number of calories needed per day. M by men in age group X.
All right, would you repeat the last three words? Age?
Age group X.
So what does X stand for? Your age, not your age. Your age what? Group. So let's go back to the graph, and you find your age group number. Your age group number. Now, the horizontal axis on many of the graphs are not what you think they are at first glance. You have to read carefully what it's standing for. Often, if you're tracking the growth of some price versus time, say since the year 2010, then the horizontal axis will be the years since 2010. 1, 2, 3, 4, 5. So you have to read this fine print about what the x-axis is standing for. In this case, it's your group number, which would be 1, 2, 3, 4, 5, or 6. Yes, sir.
I'm just saying I got one answer. I said I got one answer.
You got yours.
Yes.
What do you collect needs from me?
2,662.
Yes, that's about what we'd expect, right around 2,000. Okay? So, we're through now with our exposition of what models are. So I'm going to go into some of the content for this chapter 2. I'm going to write 2 items on the board. 3x equals 9. Notice our first algebraic equation. And this one, 2x plus 3y. Now, one of these items is an algebraic equation. The other one is an algebraic expression. Now, which one is which? Hint, equations have equal signs. So which one is the equation? So this is the algebraic equation. This is an algebraic expression. Now, equations have solutions. There's only one x that makes this be true. And we have found it when we have an x on one side of the equal sign, and the answer will be on the other. So we need to go from the equation as we are given it to having an x by itself. We need to strip everything down. So here we have 3x, here we have 1x. So what is it that's causing trouble? The 3. Now, when we are given the problem to start with, we are told with assurance that at that time the left side is equal to the right side. The left side will continue to be equal to the right side so long as we do the same thing to both sides. For example, if there are the same number of people in this room as there are in the room across the hall, if I add 10 people to each room, are the number of people in the room still equal? If I double the number of people in each room, are the number of people in the room still equal? You can do anything you want as long as you do the same thing to both sides, and the equality will continue to hold. Now, since the 3 is causing trouble, what's the relation between the 3 and the x?
Multiplication.
And what's the opposite of multiplication? So we can get rid of it by doing that, and truly it's gone. But if we do it to the left side, what do we also have to do? To the other side. So we get our answer x equals 3. Now you test that in the original equation. 3x equals 9. 3 times 3, does it equal 9? 9 equals 9, so we have done what's called the check. Now algebraic expressions are evaluated. You don't solve them, you evaluate them for given values of the parameter. For example, for x equals 1 and y equals 2, what does this expression evaluate to? Anyone? X equals 1 and y equals 2. What does 2x plus 3y equal? 2x plus 3y is equal to 8. Okay. Now we can evaluate it for x equals 0 and y equals 5. And what does it become out equal to? 15. So you see there are an infinite number of evaluations that you can make. Equations have only one solution. But expressions can be evaluated for any set of the variables at all. Now first I'm going to work with algebraic equations, and we started with this one right here. So I'm going to try another one. X plus 2 is equal to 7. I need the x by itself. So what's causing trouble? 2. And what's the relation between the 2 and the x? And the opposite of addition is, so if I subtract 2, it's going to go away. But if I do it to that side, I have to do it to this side. So here I get x equals 5. So we check it in the original equation. 5 plus 2 is equal to 7. 7 equals 7, and we're done. So your check is complete when you have some number on the left side and the same number on the right side. Now let's do 2 things at once. Suppose I have 2x plus 3 is equal to 11. Now, there's two things causing trouble, the 2 and the 3. Which one should we attack first?
3.
The 3. Why? Because experience teaches you, I've been there, if you attack the 2 first, the problem gets worse. Anyone else been there? So by experience, we learn that we want to attack the 3 first. So the relation between the 3 and the x is addition, so we nullify that with subtraction and get 2x is equal to 8. Now the 2 is causing trouble, and the relation between the 2 and the x is multiplication, so we nullify that with division, and we get x equals 4. And we check it in the original equation. 2 times 4 plus 3, does it equal 11? 8 plus 3, does it equal 11? 11 equals 11, and we get the check. Okay. So now let's take our handout page, and go to page 328, which is the back page minus 1, 328. So, no pencils. What's the answer, anyone, to number 1?
X equals 10.
X equals 10, all in favor? Okay, now, what's the answer to number 8? X equals 3. Gary, is X equals 3 for number 8? Good. Now let's try number 18. 9x minus 14 equals minus 77. Well, the 14 is causing trouble. So I get 9x is equal to what? 63, which means x is equal to 7. So you don't need me to tell you it's right or wrong.
Negative 7, sorry.
Negative 7, the minus sign is so faint, you can't see it from that deck. So we're going to confirm that by checking. So 9 times a minus 7, minus 14, does it equal a minus 77? 9 times 7 is 63. Minus 63 minus 14, does it equal minus 77? Minus 77 equals minus 77, and we have a check. So that's how we do these problems. And now the next one that I'd like to do is 28. Number 23. X minus. Dylan, do you have an answer?
X equals 25 over 3.
Okay, let's work it through. First I have to distribute this minus sign. Some of you don't like to distribute a minus sign, but let's go ahead and try it. A minus sign times a plus 2x is a minus 2x. A minus sign times a minus 10 is a plus 10. Some people feel more comfortable if you put an imaginary 1 right there, which you're permitted to always do. So you have a minus 1 times a minus 10 is a plus 10. No problem, 33. Now we have to collect like terms. We have a 5x and a minus 2x for a total of 3x plus 10 is equal to 35. The 10 is causing trouble. So 3x is equal to 25, and we divide both sides by 3, and we get Dylan's answer. X is equal to 25 over 3. Okay, good. So everyone please try 39. minus two.
39.
He said 39.
Yeah. Yeah, okay.
Oh, it's one thing to come in late, it's another thing to start conversations.
That was me.
Sorry,
I asked
sir.
him what
Got
number.
it. Okay, so this is what we're doing, number 39. On page 328. Dylan, again, your answer.
X equals 6.
X equals 6.
No?
Any support for 6? Momoko supports it. Any other answers out there? Emilio, what do you have?
I got x equals negative 6 over 5.
Original. Alex?
Got that x equals 32 over 5.
Well, we best work through this one. I'll do some steps. First, we have to do these distributions. So 5 times 2x is 10x. 5 times minus 8 is 40. And we have the minus 2. Now let's distribute this 5. 5x minus 15 plus 3. Now we can collect some like terms. 10x minus 42 equals 5x minus 12. So we've gotten this far. Now we have a momentous decision to make, and you don't want to make it wrong. We've got x's on the left side of the equal sign and x's on the right side. We now have to decide, and decide correctly, which side of the equal sign should we collect the x's on. The left side, so it's very clear, the left side. So that means this one's on the wrong side. We have to make it go away. How do you make it go away? You subtract it out. But if you do it on that side, you also do it on this side. So you get the new equation of 5x minus 42 equals minus 12. Now, the rest is old news. We have to get rid of the minus 42 with a plus 42. And a plus 42 in this part, we get 5x equals 30, and it looks amazingly like we get an x equals 6. Now suppose Esperanto was wrong. Suppose that we should have collected from the other side. We have 10x minus 42 equals 5x minus 12. But we want to collect the x's on the right-hand side. So we have a minus 10x and a minus 10x here. And we have a minus 42 is equal to minus 5x minus 12. So we add 12 to each side. And we get a minus 30 is equal to minus 5x. Now the minus 5 is causing trouble. So we divide both sides by minus 5. And we get 6 is equal to x. So you see it makes no difference whether you collect x's on the left side or the right side. So feel easy about it. And we do have the answer x equals 6. Now you notice that we have stopped checking equations we stopped when we had the 25/3. The reason we did is because this one can be checked, but the other one, x equals 25/3, is better not to check for the following reason. If you check your equation and it doesn't check, that means one of two things happened. You solved the equation wrong, or you did the checking wrong. And if the suggested answer is complicated enough, then it's at least 50-50. The answer could be right, you just did the checking wrong. So instead of getting into that quagmire, if the answer is complicated enough, you just trust it. You go slow, you be careful, and you'll get those answers. Now I'm going to write another equation on the board, and it happens to be number 47. x/3 plus x/2 equals 5/6. I hate fractions in equations. The first thing I do when I see fractions in equations is I want them not to be there. So if you already have good technique for solving equations that have fractions and it works, just keep using it. But if you're looking for a good technique, then try this one. The first thing I want to find is the LCM of the three denominators. What is the LCM of 3, 2, and 6? 6 itself. So you take that 6 and you multiply each term by it. 6, 6, and 6. Now it's mathematically valid to do that because I did the same thing to both sides of the equal sign, true? I multiplied the entire left side by 6 and the entire right side by 6. So it's a valid mathematical step. But notice the magic that takes place now. The 3 goes into the 6 how many times? 2, so we get 2x. The 2 goes into the 6 how many times? So we get plus 3x. And the 6 goes into the 6 how many times? So fractions are gone. Magic. So the technique is you find the LCM of all the denominators and you multiply each term by it and your fractions will reduce away. So here we have 5x is equal to 5 or x is equal to 1. The solution to the equation. And so I'll do one more. Z/5, this is number 50. Z/5 minus 1/2 is equal to Z/6. Okay, so the LCM of our three fractions are, it's what? The LCM of 5, 2, and 6.
30.
So I multiply each numerator by 30. And I see what kind of reductions we can get. 5 into 30 goes 6 times, we get 6z. 2 into 30 goes 15 times, minus 15. And 6 into 30 goes 5 times, equals 5z. And fractions are gone. So now we have that awful time again. Are we going to collect on the left or going to collect on the right? To make a point, I'm going to say let's collect on the left side. So I'm going to do a minus 5z on this side and a minus 5z on this side. And I get z minus 15 equals, and what's the new number for the right side? 5z minus 5z is? 0. Some people stop right there and say, I'm doing the problem wrong. I should never get a 0 for an answer. It's not your answer. So 0 is a perfectly fine number. If you generate a 0, just write it down and respect it. It's just as good as any other number. Now, we need z by itself. So how do we get z by itself?
Add 15.
Add 15 to both sides. And z is equal to 0 plus 15, or 15. So we solved that problem. So now we'll have you guys do one of this type, which is number 52. 52, please. y/12 plus 1/6. y/2 Chanel, you have an answer?
Y equals 1.
Y equals 1. Any support? Objections? Lots of support. Would anyone like to see Chanel do the steps? No requests. Y equals 1. That's how we do it. Okay, I'm going to write another equation on the board. X equals 2 equals 4. And share with you a way to do this equation. Now I say, wait a moment, you just showed us how to do that equation. It's got two denominators, I just find the LCM and multiply each numerator. There is a faster way to do equations that are of this type. This type of equation has exactly one fraction on the left and exactly one fraction on the right. When you have exactly one fraction on the left and one fraction on the right, you're permitted to cross multiply. This times this equals that times that. So we get 24x is equal to 32 times 3, or 24x is equal to 96, or x is equal to 4. So let's try another of these ones that are susceptible to cross multiplication. 24 over x equals 12 over 7. So is this equation susceptible to cross multiplication?
Yes.
It has a single fraction on the left and a single fraction on the right, so the cross multiplication lamp is lit. So this times this equals that times that. So 12x is equal to 168. And so x is equal to 14. Now I'm not just pulling this out of my rectal database, because I'm going to show you now a generic proof as to always, when you have one fraction on the left and one fraction on the right, you are permitted to cross multiply. So let's take any generic fraction on the left, a over b, where a and b can be anything at all, just one numerator and one denominator. It is equal generically to c over d, where c and d can be anything at all. Now, I'm permitted to do anything I want as long as I do the same thing to each side. What I choose to do to each side is to multiply b times d. And what you observe is on the left side, we have the b's cancel, and we get a times d. And on the right side, we get the d's cancel, and we get bc. So it's always generically true that whenever you have a over b equals c over d, it's equivalent to a times d equals b times c. So this is your first mathematical proofs. There are harder ones, but this is how a mathematical proof is done. So let's have you try one. First I'll do one more for you. X over 7 equals x plus 14. No, let's have you do one. 66. X over 64 equals minus 9 over 16. Calculators are encouraged. And Alex, your answer, please.
X equals negative 36.
We'll see. Chanel, answer?
X equals negative 36.
Negative 36. Mercedes, negative 36. All in favor, negative 36. Anybody want to see Alex do it? No, it's straightforward. Okay, now I'm going to do one more of a type. X over 7 equals x plus 14 over 5. Does this equation qualify for cross multiplication? Yes or no? Well, the left side has one fraction, agreed? Because it has one numerator and one denominator. One numerator and one denominator equals one fraction. On the right side, how many numerators are there? One. . 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. because it's above the division sign, that's the definition of the numerator. So there is one fraction on the left, because remember, A, B, C, and D can be anything at all, as long as there's only one division line, there's only one fraction. So cross multiplication is in effect. So, but you have to be sure to multiply the entire denominator by its entire numerator partner. That means this 7 multiplies the entirety of that numerator, meaning parentheses, x plus 14. Be sure to catch it all. So now we proceed. 5x equals 7x plus 98, and so 2x is equal to minus 98, and x is equal to minus 49. Okay, now I'll have you do one for me, which is number 71. So number 71, does cross multiplication apply to this problem? Yes, it does. One fraction and one fraction, no matter how complicated.
This is
71, same as my IQ. Okay, do somebody else. Jeremiah, please.
Y equals 10.
Y equals 10, all in favor of 10. Anybody like to see Jeremiah do some steps? Still no requests. Y equals 10. Okay. Now, now we're going to give Como a choice to make. It's going to be a new topic. Como, we have a lake on base. You've been there, seen it? Lake has fish. Como, the colonel calls you into his office and says, Como, I want you to tell me how many fish are in that lake. Have you ever tried to count fish? They're pretty quick, they change places. You don't know what ones you've counted, what ones you haven't counted yet. So counting fish is really ridiculous. So Como sees one stripe disappearing quickly, but we come up with a technique for counting wildlife, which is called tag and sample. Tag and sample. So the first thing we do is we let x equal the number of fish in the lake, the total number that you're trying to find. So we're going to set up one ratio for the lake in general. So what Como does is he goes out in a boat with a net to the middle of the lake, and he scoops up a net full of fish. And he counts the fish in the net, which isn't too hard. There's 125 fish in the net. And he gives everyone a tag. He tags them all. And he releases them back into the lake. So now in the lake, we have X fish and how many tags? So the ratio of tags to fish in the lake is 125 to X, agreed? So now Como waits a week until those 125 tagged fish circulate, they're randomly distributed throughout the lake, and he goes out again. And now he scoops up a net of fish at that time. So this is called the sample. Now in the sample, there are 90 fish. And he finds 20 tags. And now he makes the assumption that the ratio of tags to fish in his sample is representative of the ratio of tags to fish in the whole lake, because it's a random sample, agreed? So he now says that the percentage of tags in my sample is the same as the percentage of tags in the whole lake. That means that the ratio of 20 tags to 90 fish in his net is the same as a ratio of 125 tags to X fish in the whole lake. Do you think of any mathematical operation that permits you to solve this equation? Cross multiplication. Let's go ahead and do it. So we get 20 times X is equal to 125 times 90. Hi, I'm gonna do 125 times 90, 11,250? I did it this morning. 20X. So X is equal to what number?
$562.5.
So say 563. So now there's a choice. You could have found out that there were 563 fish in the lake by doing it this way, or you could have waited out there and tried to count them all yourself.
That's you.
Sure.
Where'd you get the 90 from?
Well, if you listen, he went out a week later with the same empty net. He put the net in the water and he scooped it up and he counted the number of fish in the net. There were 90 fish in the net.
Okay.
In the sample. So he made a sample of size 90. Arbitrary. You don't know how many fish in the net, doesn't matter. And of those 90 fish, he saw that 20 of them had tags. Of the 90 fish in the net, 20 had tags. So then he assumes that the sample has the same ratio of tags to fish as does the entire lake. So he sets up this proportion. So let's try a problem from your handout, page 327. Let's do example 9. So the way you do these examples is you take a sheet of paper and you cover up the solution. So example 9 at the top of the page. Top of the page, example 9. Wildlife biologists catch, tag, and then release 135 deer back into a wildlife refuge. So how many tags are there in the entire refuge? And how many deer are there in the entire refuge?
We don't know.
X, right. And then he comes back later, 2 weeks, and he observes a sample of 140 deer, 30 of which have tags. You now assume the ratio of tags in the sample holds as the same as the ratio of tags in the total population, and you set up your proportion. There will be a problem of this type on your final. The guy that makes your final up loves counting wildlife. So you do your cross multiplication and you get your answer, then you lift a piece of paper and see if the author got it right. Como, did the author get it right? 6:30. 6:30. Okay, now please do checkpoint 9. Checkpoints are the ones that just have the box with a number in it. Checkpoint 9 in the middle of the page. And we know how to do these. So Kelly, you have an answer for checkpoint 9, how many deer?
I got the answer, but I wanted to check it first. But I'll say it, I got 720.
No need to check it, it's the answer we're looking for. All in favor of 720. Let's take a break. So 5:40, please. Well, I guess Good. All right, but you saw it a moment ago, didn't you? No, I found it, double up, right here. Nope, it's not it. Okay, you check my file, I'll check yours. Hi. So we're gonna do all of this for next time. That's what we'll do, and tonight's assignment's gonna be A4. And the video will be out there, and, okay, right, okay. Thanks, Kelly.